Now let's look at series. Now, when we talk about series, normally we're not concerned with what the sum actually turns out to be. When we have a series, we're not concerned with what exactly is the value. What is this infinite sum's value? We're just simply concerned with if it converges or diverges. However, there are some exceptions. There are the telescoping series and the geometric series. In those cases, we can actually find the sum. So uh, we can go further than just determining if it converges. Now, this right here is an example of the telescoping series. What we need to do with this before we go any further is we need to rewrite it using partial fraction decomposition. So what we would do is we would take this, make sure the bottom is factored as it is, and we decompose it. Okay, so here we've got a over 2n plus 5 plus b over 2n plus 3, like that. And then we go about the usual business of partial fraction decomposition. Just set it up the usual way. Now, um, I think so I'm going to go ahead and be consistent. I'm going to use equating of coefficients. So I got negative 2 equals 2an plus 3a plus 2bn plus 5b. Now, the coefficients of n, which are 2a, whoops, a pen went crazy. Okay, let's see here. Okay, so here's what we've got. We've got 2a plus 2b. That has to equal 0 because there's no n over there with the negative 2. So 2a(n) plus 2bn. Those coefficients, 2a plus 2b, those have to be 0. And then we have 3a plus 5b. It's like 5b. That has to add up to negative 2. So now we have a system of equations here that we can solve. And of course, we could use whatever method we have to solve systems. However, if you look at this, it's pretty obvious that um, A and B need to be opposites. And if I notice, if A is 1, B is negative 1. And let's just see if that works. Just looking at this first equation, it looks like that's going to work. Now, if I go down here and put in a 1 for A, I get 3, a negative 1 for B, minus 5, I get negative 2. Yeah, so this works. So our partial fraction decomposition is A is 1 and B is negative 1. So now we've got our sum. Our sum is going to be n equals 1 to infinity of, let's see here, 1 over 2n plus 5 minus 1 over 2n plus 3, like that. Yeah, that should do it. Now, what we can do is we can start generating our partial sums. So let's look here. Let's look at the first partial sum. The first partial sum is when n is 1. So we get 1 over 7 minus 1 over 5. That's our first partial sum. Now, we look at our second partial sum. Now, remember, our second partial sum is going to be the first partial sum and then the next term. So plus, now when n is 2, so we get 1 over 9. See, 2 times 2 is 4 plus 5 minus 1 over 2 times 2 is 4 plus 3. That would be 7. Okay, so 1 over 2 times 2 is 4 5, 6, 7. Yeah, there it goes. Now, I notice that looks like let's go ahead and generate some more terms here, but you can see this 1/7 and that negative 1/7 on the end. Looks like they're going to cancel. Let's do the third one. We get 1/7 minus 1/5 plus 1/9 minus 1/7. Now let's put in the 3 plus 1 over 6 and 5, that's 11, minus 1 over 6 and 3, that's 9. Okay, now let's just take note of some things here. First of all, notice these 1/7s cancel, these 1/9s cancel. So it looks like what we have here, let's just take note. We've got negative 1/5, okay, right there, plus 1/11. Now let's see what we've got up here. Let's look here. These ones cancel, and we're looking for a pattern here. We've got negative 1/5 plus 1/9. Okay. Now I want to see if I can generalize this a little bit. N- So if we think about this, negative 1/5 plus 1 over 9, and down here, negative 1/5 plus 1 over 11th, we're just looking for how those compare to these subscripts, 2 and 3. So let's see if we can come up with some kind of general form here. Let's say S sub k. I think this negative 1/5 is there to stay. I don't think that one's going anyplace. But let's see what happens over here with this one. With this, let's see here, 11. Let's see here. What if we do 3 times 3 plus 3? That's 9, 10. Well, 3 times 3 plus 2, 9, 10, 11. So let's think about this. 3n plus 2. What about this one over here? 3 times 2, 3 times 2 plus 2. That's 6, 7, 8, 9. It looks like this formula might be 1 over 3n or 3k plus 2. It looks like that might be the formula that we're looking for. Okay. Now we could try some others, but uh, I think that's going to work out. Let's see if it works for this first one. We have 3 times 1 plus 2. Let's see. Um, Now that doesn't work for the first one, but it works for these others. So the fact that it doesn't work for that one kind of says, well, maybe this isn't what, maybe that's not what we're looking for. Well, notice if we look back up here, notice we've got 2n plus 5. Ah, now notice that's going to be a clue for us. When we're trying to find a pattern here, look up to your original partial fraction decomposition. And let's see if 2n plus 5 works. Well, let's see here. 2 times 1 plus 5 is 7. Ah, that works. Let's try this one down here. 2 times 2 plus 5. Of course, that's 9. Of course it's going to work. Uh, 2 times 3 plus 5. Yeah, 11. Yeah, it makes sense that that would work. So when you're trying to find this pattern, look back up at what, your original. So this is 1 over 2n plus 5. Now, if we take the limit of that, we'll get our sum. The limit as k goes to infinity of negative 1/5 plus 1 over 2n plus 5. Well, this thing right here goes to 0, and you're just left with negative 1/5. And that is what that series adds to. Okay, now let's look at a geometric series. And a geometric series, that's another one that we can determine if it converges. And not only determining if it converges, we can figure out what it converges to. So for example, this one right here, Well, notice the common ratio here is less than 1. So we know that converges. So here's what it converges to. On the bottom, we've got 1 minus 1/2. Now on the top, it's going to be the very first term in our series. In other words, when I put a 0 in for n, I get a 3. So there it is. So we get 3 over 1/2, which is 6. So that series, not only does it converge, it converges to 6. Now, we start talking about just determining if a series converges. And we're not, for most series, we're not concerned about what they converge to. And we have these tests. First of all, we have the comparison test. See, comparison test. And we have the direct and the limit comparison test. And so let's look at how we would work our way through these. Let's suppose that we have this series, and we want to know, does that series converge? Well, we suspect that it does converge because we know 1 over n squared converges, because that's a convergent p-series. So we compare these two. We take 1 over n squared plus 1, and we compare it to 1 over n squared. In fact, 1 over n squared plus 1 is less than 1 over n squared. Okay? As you're adding these numbers, you notice that if I put in n squared plus 1, 1 over n squared plus 1, it's going to be less than 1 over n squared. And here's the thing. We know that this right here, this one, this converges by p-series. That's how we know that one converges. And since 1 over n squared plus 1 is less than 1 over n squared, we know this converges by direct comparison. So the one series is less than the other. So if the one converges, then that one converges. Now we're assuming, of course, that these are positive term series here. Now let's look at another one, 6b. So we've got this one. 1 over the square root of n minus 1, n goes from 2 to infinity. Now, same process. We suspect this one diverges because it's got this square root in the bottom. And remember, when we're talking about a p-series will diverge if the p is less than 1. So we're thinking of this. We're thinking of 1 over the square root of n. And we're wanting to compare that to 1 over the square root of n minus 1. Now, this 1 over n, the square root of n, is less than 1 over n squared minus 1. It's less than. And this series right here, it diverges by, p-series. So if that one diverges and it's less than the other one, it's less than this one, then this one must diverge by direct comparison. Direct comparison. Okay. Okay, now let's look at another one. Let's suppose, let's see here. Let's suppose we're looking at 6c. So we've got this one. And we've got n over n cubed plus 2n plus 1. That's a cube up there. Now, with one like this, using direct comparison can be a challenge. But we have limit comparison. Remember, with limit comparison, we find a b sub n. And the way we find that b sub n is we take the thing up top that's the strongest, the most dominant, and put it over the most dominant on the bottom, and we get 1 over n squared. Now, that's a series. Now, here we want to get something we know something about its convergence. And in fact, we know that 1 over n squared, we know that this converges by, it's a p series. So we know that converges. So now we're ready to do our limit comparison. We take the limit as n goes to infinity of n times n cubed plus 2n plus 1 divided by 1 over n squared or multiplied by n squared over 1. And let's see what that gives us. That gives us the limit as n goes to infinity of n cubed over n cubed plus 2n plus 1. That limit is 1, the ratio of the leading coefficients. Now, the limit comparison test tells us that if your limit is finite and bigger than 0, they both either converge or diverge. This one converges, therefore this one converges by limit comparison test. So there's the comparison test. Now, we also have the integral test, okay? So integral test. It's another test we encountered. So let's look at this one. So we've got, whoops, got ahead of myself. Let's look at the sum, okay? So we've got n goes from 1 to infinity, 1 over n squared. Now we've been working with this one. We observed earlier that that one converges by, well, in this video, I've just assumed we've encountered it and we know it converges. I've assumed we know about the P series, but let's go ahead and see if we can figure out, use the integral test to determine if this converges. What we would do is we're going to integrate from 1 to b and take the limit as b goes to infinity. In other words, we look at this improper integral of x to the negative 2. See? Instead of 1 over n squared, I got 1 over x squared. Now, if we go through the process here, we're going to get the limit as b goes to infinity of negative 1 over x, and we're going to go from 1 to b. And of course, this is going to be the limit as b goes to infinity of negative 1 over b minus 1 over 1. Well, this goes to 0, and this is going to be 1. Converges. Therefore, this converges by the integral test. Converges by the integral test. Okay. Now let's look at another one here. We've got 7b. So we've got this series. N goes from 1 to infinity, 1 over n plus 1. And we write this as an integral from 1 to b, the limit as b goes to infinity. And this is going to be 1 over x plus 1. Well, dx. Don't forget the dx there. So this will give us the limit as b goes to infinity of the natural log of x plus 1 from 1 to b. Well, we can see right away that's going to diverge because we've got the log here. So we've got the limit as b goes to infinity, log b plus 1 minus log 1 plus 1. This one, that diverges. Now, as soon as we see part of this diverge, we're done. So this one here, it diverges, okay, by the integral test. Now, let's look here. We've got 7c. Okay? So we've got 1 over n squared plus 1. Now, we rewrite this, the limit as b goes to infinity of, here we go, 1 to b. And this one is going to be the limit as b goes to infinity of arctan of b minus arctan of 1. You know, kind of went through it fast, but the antiderivative 1 over x squared plus 1 is arctan. Now we know that this right here is pi over 2 minus pi over 4. So it looks like we got pi over 4. So that's a number. This converges. So this converges. Now let's look at the ratio and root test. First of all, the ratio test for this one. This one's whenever you see an exponential function or an exponential expression and a factorial together, you're thinking, root test. I bet I'm going to use, I mean, the ratio test. I'm thinking I'm going to use the ratio test. So here we go. We got the limit as n goes to infinity of 2 to the n plus 1 over n, whoops. Let me go ahead, instead of writing uh, n plus 1 factorial, let me write n plus 1 times n factorial. So I just did a shortcut there. And then up here, it's n factorial over 2 to the n. Now, notice that these cancel, and this little n's gone. So let's see what we got now. We've got the limit as n goes to infinity of 2 over n plus 1. That equals 0, which is less than 1. Therefore, it converges by the ratio test. It converges. Now, this one over here, this one looks a little bit different. This one might be a challenge to use the straight up ratio test. However, we can do the root test because notice this is 2 to the n over n to the n. That just seems perfect for taking the nth root. So what we've got is the nth root of 2 to the n over n to the n. And that's just the limit as n goes to infinity of 2 over n, which is 0, which is less than 1. Therefore, it converges by the root test.